All right, so here's a different example. It's also a polynomial example, but it's actually a little bit more complicated. So let's do the same type of analysis that we did before. I'm going to do this a little bit quickly, trusting that you can do this on your own, the details. But if you just look for zeros and sine of x to the 4 plus 3x, you should find that you get 2 zeros. You can factor that. And factoring it will give you a 0 at 0. And it'll also give you a 0, maybe I need a little bit more space, at minus 3 to the, no, oh yeah, minus 3 to the 1/3. Okay, and so those are 2 zeros of the function. And then we ask the question, what is the sign between those and beyond those zeros? So if we're out here, I won't include the intervals, but this here is going to be to the left of minus 3, and this is between the zeros, and this is above 0, x equals 0. And so when x is negative, we get a positive value out of this. And we can see that without doing a lot of work. We can see that asymptotically, the x to the 4 is going to be larger than x to the 3, the 3x. So for large enough negative numbers, this ends up being positive, but it can't be 0. We found all the zeros, so it can't be changing sign until we get to this 0. So that means it's positive all the way. And then at x equal minus 3 to the 1/3, well, this is a little bit, tricky to maybe to see. You have to factor that and figure out or evaluate at points, but you should be able to determine that that's going to be negative in between. And then on the other side, it's going to go positive again. Okay, so let's see what we can figure out about f prime now. So f prime of x, that one is going to have a single 0, and it's going to be at minus 3 over 4 to the 1/3. And this one, it'll be 0 there, and this one, if x is a positive number, then this will be positive, and so that means that everywhere above minus 3 over 4 to the 1/3 has to have the same sign, so it's going to be, oops, so this is x greater than minus 3 over 4 to the 1/3, positive here, and down here, x less than minus is going to be negative. Okay, so right away we can see the first derivative test tells us that x equal minus 3 over 4 to the 1/3 is a, let's see, the slope is negative and then 0 and then positive, so this is a min. So we have success out of the first derivative test right away. That's great. If you take the second derivative and plug it in, you can see no matter what, it's going to be positive, and that also tells us that we have a min, because a positive second derivative means the first derivative is increasing. If the first derivative is going to go through 0, it has to have started negative, increased to 0, and then increased to a positive. All right, so now to the tricky one. What do we have in the way of inflection points for this function? So let's do a table for that. So we have x and we have f double prime of x. And now f double prime has a single 0 at the origin. And for x less than 0, we can see that the f double prime is positive, and for x greater than 0, we have x double prime is also positive with this 0 in between. So what does this mean? We found a point where f double prime was equal to 0. It's tempting to say, oh, we must have an inflection point there because the second derivative is 0. But that's not always going to be true. And what I mean by that is f double prime being equal to 0, there's a few different things that can happen. So what the way I would interpret this is f double prime is f prime prime, right? And so when you find a 0 in the derivative of something, that means you might have a min or a max of that function. So f double prime equals 0 means that f prime could have a min or a max. What is a min or a max of f prime? So if if f has some slope, so f prime is equal to some number, let's say a positive number, like a positive slope here. What does it mean to have a max? It means that before that point, the slope was lower, and the slope increased, and then after it decreased again. So that would be a maximum in f prime, right? Low slope, high slope, low slope. And so f double prime being 0 could correspond to one of these. It could also correspond to a minimum, meaning that it was steeper before, it came to a lowest slope, and it got steeper again. So that's a different type. And you can see here, this is going from concave up to concave down, and that corresponded to a max in f prime. Here we go from concave, we go from concave down to concave up, and that corresponded to a min of f prime. And then there's also the negative versions of these. So we could also have had a negative slope in f, and we could have had a lower slope before and then a lower slope after. This would be going from concave down to concave up, and that would correspond to a min in f prime. And then we could, because we have a negative number, an even lower negative number, and then back to a less negative number. And then we could also have a steeper drop initially, mellowing out, and then getting steeper again. So this would be concave up, concave down, and that would correspond to very negative coming up and then dropping again. So this would be a max in f prime. But the value here, then the f prime is negative. F prime is negative in both of these cases. And here f prime is positive. Okay? So these are the four scenarios that we can have for an inflection point. Which do we have here? We don't have a change of sign. We're going from concave, so second derivative positive means concave up to concave up. And that's none of these scenarios here. What is this scenario? All of these ones would correspond to a min or a max in f prime. And what we just found is an inflection point in f prime. And so what does an inflection point look like in f prime? Let me erase all these. So an inflection point, an inflection point in f prime, not in f, means that we have 0 here at the origin. On one side, we have a function that is increasing. So we're above this 0 here. We're in this interval here, so f prime is positive, because the origin 0 is in this interval here. And so we're increasing before, but we are concave up, which means the slope is increasing. And then if we had an inflection point, it would go concave down, but we're not doing that. We are going flat as though we're about to switch to a different concavity, but we're not switching to a different concavity. And so you can see the way you construct these functions is actually by taking very flat functions whose first and second and third derivative even are 0, and adding to them 3x. So if you take x to the 4, it's a very flat function at the origin. And when I add 3x to that, I'm subtracting from this side and I'm adding to this side. So the whole thing tilts. And what I end up with is a function like this. This is x to the 4 plus 3x. And you can see now that this here is the flatness here is why the second derivative is 0. But just like x to the 4, it doesn't change concavity. And so this is what our graph looks like. You can see here is that min. That's going to be the min that we found up here using the first derivative test. And here is this non-inflection point. It's a non-inflection point that's quite flat, but the concavity doesn't change. Okay, so the take-home message from this whole video is that when you're looking for inflection points, just like when you're looking for mins and maxes of f, you don't always find mins and maxes at flat spots. You sometimes have inflection points in f. And then when you're looking for inflection points of f, you're really looking for mins and maxes of f prime. And whenever you're looking for mins and maxes, you may find one, but maybe not. And so that's why we either have an inflection point that's concave down to concave up, or an inflection point that's concave up to concave down, or an inflection point that's concave down to concave up, but all negative, or an inflection point that's concave up to concave down. These are all cases where we have, let's see, this is a min in f prime, a max in f prime, and so on. But the scenario that we're in, which is this one right here, is where you don't have a min or a max in f prime. Turns out you have an inflection point in f prime, which means you do not change concavity. Okay, so I will continue with another couple of videos on these power functions, but with rational powers. Yeah, that'll be in the next video.